All right. Last time we talked about the difference quotient, which was simply we found that that was the slope of a graph at any point xy. Traditionally, to find slope, we needed 2 points. We needed x1, y1, x2, y2. And now for this part, that only works for linear equations. Now for this, these work for curves. So the problem we have is what happens at the point where h is equal to 0? Or what happens to the curve? What value does the function approach as it's getting closer to h equals 0? Remember what h equals, what the formula for h was. What is the value? What is the equation for h?
H by itself, like zero.
No, equation, not value. What is the equation? What does h represent? We talked about it last week.
Y.
You're just guessing. If you don't know, then don't guess. H is the distance between x1 and x2. Because remember, to find the slope of a curve, we can only have 1 point. So what we have to do, we have to get x2 as close to x1 as possible. So we know that x1 plus h will give us x2. So the formula for h is x2 minus x1. So the closer x2 and x1 get closer to each other, what value does h get? As x1 gets closer to x2, what value does h get? It's basic math. As x1 and x2 become the same value, what does h become? What's that? 0. H gets closer to 0. Because remember, h is the distance between x1 and x2. If they get close to each other, the closer they get, the distance becomes closer and closer to 0. Can it ever become 0? Well, remember, look at our formula. No. Since h cannot equal 0, we need to see what happens as h gets closer to 0. This symbol means approaches or gets closer to. The arrow represents gets closer to. So we know that x1 cannot equal x2 because h is x2 minus x1, and that would make x equal 0. But as it gets closer, closer, closer together, infinitely close, it does approach a value. So as x1 approaches x2, the slope of the function approaches some value. And we call that value the limit. That's what this whole section is about. Okay, if you can't see the board, remember, your chairs have wheels and there are lots of empty chairs over here. So example 1. How does the function f of x, okay, so we know that we're talking about what does this represent? We talked about it last week. What do these symbols represent here? The change of y over change of x. What does that represent? Slope. So we're looking at the difference of y and the difference of x, which is a slope. In our example, equals x squared minus 1 over x minus 1. So how does this function behave as, well, how does the function behave when x is near 1? So we're saying that when x equals 1, how does it behave?
Point there, like, is near, are you saying near or near?
Near.
You look like
M has 3 humps. N has 2 in cursive.
So this is that's an N?
Yes.
You
In
look-
cursive, this is not English class. So
Oh, okay, I see.
in English class, M has 3 humps, N has 2 humps. So this is not English class.
Okay,
So what happens to the function as if x equals 1? Or what happens as it gets near 1? Anybody have an idea? Any guesses? This is supposed to be calculus 1.
it's like zero.
The rest of the class, what? What happens when x equals 1?
Just equal to 1.
How did you get that? How did you guys get 1 as an answer?
Well, taking what the thing I know is that you actually just divide it. You divide it by the.
No.
X back- X
What
back-
this thing tells you, okay, let me review algebra here now,
Okay.
since you guys obviously are very deficient in that then. So what this says, when x is 1, what happens here? Plug in 1 in place of x. It's not that difficult. So what happens? Work it out.
That becomes a zero.
Anybody else? You can be what?
Like your result is gonna be doing, or like, it's not X.
Well, give me some values. Give me numbers. What does the top become? 1 squared is 1. 1 minus 1 is 0. 1 minus 1 is 0. It's undefined. Does not exist. Yes. But we're going to learn a rule in a little bit that whenever you have rational expressions and you get 0 over 0 or infinity over infinity, that tells us one thing. What does that tell us? Don't take guesses. I want legitimately thought out answers. Remember, x is equal 1. I put x is 1. I got 0 over 0. What does that tell us? Well, the final answer becomes undefined. But for both the top and bottom to be 0, when x equals 1, that means they have to share the same value at that point. So they have to share something. Let's look what happens here. What can you do with this equation? Factor it. What is, if we factor it, what do we get on top? That's it, x plus 1. It's a quadratic equation. That means there's 2 solutions. It's the difference of 2 squares, x plus 1, x minus 1. That's the factor of the top. And the bottom is already factored out, x minus 1. Because we get 0 over 0, as I've said, you have to have something in common. And yes, they do. They both have an x minus 1 in common. So this function can be simplified. That's what the graph of the function is going to look like. The graph of this function the y-intercept is at 1. The slope is 1 over 1. except that's just the line, but what do I have to do here? That's not the true graph of the function. I have to do something else. This goes back to algebra. What value can I not use in this function? What's my asymptote? What am I, the domain of my function? Not -1. So we know that x cannot equal 1. What happens if x equals 1? What's the value? If we put 1 in there, we get 2. At that point there, we have a hole. Because remember, we simplified the equation. Now this is the equation we're looking at. That's the graph of the function. Since we can't use 1, we removed it. When you have something the same in bottom and top, when you remove it, that's called a hole. Because I removed x minus 1 from top and bottom, which means since I cannot use 1, what value would, if I plugged it in there, 1 plus 1 is 2. So that the value 1, 2 is equal to a hole. Did you not learn that in algebra? So that whenever you have a rational expression and you cancel the denominator with the numerator, and it's a function of x, that's what's called a removable discontinuity, because you can't equal 1 on the bottom. X cannot equal 1. So when I remove it, the graph looks like this equation, but I cannot use that value there. But that's okay. As x approaches 1, what's the value of the function? As x approaches 1, as x approaches 1, f of x approaches what value? I'm not saying is equal to, I'm saying it's getting closer. When x is getting closer to 1, what value y do we get? 2. That's called the limit. That's called the limit of the function. The limit of the function is simply the value the function approaches as our x approaches some other value. Let's put an informal definition to this. So as we just said, as x approaches 1, then f of x approaches 2. Remember, this is our limit value. So this is how we represent it. Instead of writing the word limit, we write LIM. As x approaches some value c, the function of f of x equals some value L, the limit. So these two represent the same thing. So in our expression here, what would be the value of my c? 1, and my limit value would be 2. Let's look for another example here. So what if I gave you this? What would that equal? Very good. Now, what this is telling us graphically, so how do we graph this equation? Let's look at here's what does this represent? It's my function, f of x. And this is the value c. That's what I'm approaching. This is my limiting value. So I'm going to graph this function. The y-intercept is at 2. 1, 2, 3 over 1. So this is my value c, and this is my value L. As I get closer to my value C, it should be up there. As I approach C, it will approach the value what? As I get closer to it, it's getting closer and closer and closer to my limit. That's from the left side. If I approach my C value from the right, what happens there? It's approaching what number again? It's approaching 8. So a limit value doesn't have to exist. Remember, we had a hole last time. It doesn't have to, it just simply has to approach it. It doesn't have to exist at that location. It simply has to approach the same value from both sides. Here we have 3 examples that will tell us the same value. So in this one, as x approaches c, what does my function approach? What limit does it approach? No. In this one, as x approaches c, what is my limiting value? L. It's a good guess. But think about what we just said. As we get closer to C, from this side, or we're already past 1, as we're getting closer to C, we're approaching this value here, which is L. And same thing from this side. So again, it doesn't matter if a value, it's some discontinuity. It's where does the function approach as a whole picture? How about this one? As x approaches C, what is my limiting value? Yeah. You notice they all have the same limiting value. This one, it doesn't exist. This one is somewhere else. And that one is, why? Because the concept of limits simply says it doesn't have to exist. It simply has to approach it from both sides. So for the limit to exist, the value has to be approached from both sides. Here's the next example. Oh, here it is. So obviously, whenever you have questions with limits, always just plug in the value first, like you did earlier. If it works, it works. If it doesn't, then we do something else. Example 3. What is an identity function? What is an identity function? From algebra. That's the function. Y equals X. So in this case, what would that one equal? Well, let's look at this. Let's look at another example. What this thing says, it's X. If X approaches 3, what's my limiting value? As X approaches -5, what's my limiting value? -5. As X approaches 0 of my identity function. So for an identity function, no matter what X approaches, it equals that value because Y equals X. Whatever X you're approaching, that's what the value is going to equal. So if you have a function like this, it's just whatever your value is approaching. That's called identity function. Another of the basic functions are constant functions. some value K, some number. It's a constant. So what this is saying is this. As X approaches, let's say 3, and my constant function is 2. What's my limit? You sure? How did it become 3? Did you plug it in? What is this? Remember, this is f of x. If f of x equals 2, what does that graph look like? And don't say a line. It's a horizontal line going through 2. So no matter what value c I give you, what is it always going to approach? 2. So in this case, it's always going to be 2. How about this one? So whenever you have a constant function, it's always going to become that. Those are the most basic ones. We're going to build up from there. So if it's a identity function, I mean just a diagonal line, it's always going to be whatever value x you're putting in there. If it's a horizontal line, then it's always going to be that value k, the constant value. And it's undefined. Is discontinuous. I don't say even find this yet. Discontinuous functions. This is example 4. Find the limit if it exists as x approaches 0. How about this one? What would that one be and why? If you're taking a nap, do so at home. So what's that? As x approaches 0, what's the limit of this function? It may help if you graph it. If you graph it, what's it going to look like? What kind of equation is this? It's got a name. It's called a piecewise defined function. It's defined in certain intervals. So the top part, what is this telling us? What does that tell us? Anybody? No. Good try, but no. These are called piecewise defined functions. Did y'all learn that in algebra or pre-cal? What this thing says, these are my functions. This is my domain. When x is less than 0, my function equals 0. So it's less than 0, so it can't be 0. And it goes for anything less than 0, for any x less than 0, my answer is 0. I'll make that one 0 also then. When x is equal to or greater than 0, the function is 1. So what's the limit as x goes to 0? What'd you get? Ooh, you're half right, but half wrong. Remember, you have to go both directions. If we're going from the right, here's 0. If we're going from the right, what is the value of the limit? It equals 1. It's this line. If I'm approaching it from the left, what is the value? 0. So if I'm going this way, it's 1. Are they equal? Are they the same value? No. You have a jump discontinuity at that limit value, so there's no solution. This is called a jump discontinuity. Because at 0, when x is 0, it goes from the y being 0 to y being 1. Is it a continuous function? No. So now we have another concept to look at. Earlier, when we had our equation, x squared minus 1 over x minus 1, is that a continuous function? This was a tough one because remember the graph of it is in essence a straight line, but we have a hole there. So we could look at a form of continuity. It's continuous to both sides, but at that value, it's got a hole in it. But this one, there's no way we can fix it. Because on this side, we're at 0, then we got to jump up here. There's no way we can make it continuous. We got to jump discontinuity. All right, let's look at another example. G of x is equal to 1 over x over 0, to 0. This is when x does not equal 0. This is when x equals 0. What do we notice about this graph? So when x is equal to 0, what do we get? 0. This is my f of x. This is my domain. These are my x values. So when x is equal to 0, y is equal to 0. So we have a dot there. When x does not equal 0, we have to use this function. Think back to the library of functions. What does that graph look like? When x is 1, we get 1. When x is 2, what do we get? A half. When x is 10, what do we get? 1/10. When x is a half, what do we get? 2. When x is a 10th, and negatives look like this. So as x approaches 0, because remember all of these we're going as x approaches 0, do we have a limit? As x approaches 0, do we have a limit? From the right-hand side, as it gets closer, closer, closer to 0, what is my y value? My y value is going to infinity. As x gets closer to 0, the y values keep on getting higher and higher and higher. From the right side. From the left side, the closer I get to 0, I get negative infinity. They become infinitely large. And at 0, it becomes 0. So there's another discontinuity. And the last one, all right, so let's look at the graph of this one. When x is less than equal to 0, our value is 0. So we have a dot there, and it goes on forever this direction. But when x is greater than 0, we have to use this function, sine of 1 over x. Because remember, what is the sine of 1 in radians? Yeah, it's just this the first third. So take pi divided by 3, you get 1.07 or 1.04. So what happens here, between 0 and 1, this thing is very, 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 very sporadic. And then after 1, it dampens out. Because the value, as x gets larger, this becomes smaller. So the sine of a smaller number becomes even smaller and smaller, 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 smaller. Because the angle gets a lot smaller, 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 smaller. We call this an oscillation. If a function is oscillatory like this, then it doesn't have a limit because you can't precisely tell me at one point is it a maximum or a minimum. But yeah, sine has a limit between 0, -1, and 1. The maximum minimum has to stay between there. But between 0 and 1, it's very, very, very sporadic, and then it dampens out. So those are examples where the limit doesn't exist. If it's a discontinuity if it goes to infinity or if it's oscillatory. The laws of limits. What's funny is these 7, 8 rules we're going to talk about now, we're going to expand them on all sorts of other things in calculus. The only thing is, it's going to be the same concepts, it's just the symbols will change. So, first off, let L, M, C, and K be any real numbers. What's a real number? What constitutes a real number?
All the way to n.
There's much more than that. This goes back all the way back down to elementary school. Real numbers consist of whole numbers, natural numbers, the counting numbers, integers, rational numbers, complex numbers. So that's what those are. So it's anything between negative infinity and positive infinity. That's a real number. So here's our first one. The sum rule. Sum rule says is this. Is the limit as x approaches c of f of x plus g of x well, let me define these also. The limit as x approaches c of f of x, that equals L. The limit as x approaches c of g of x, that equals M. So what this thing tells us is if we have a sum, a limit over sum, we can split them up. In other words, you could say we distribute. So that becomes L plus M. So if we have a sum of two functions and we take the limit, we could just take the limit of each one separately. It works also with differences. We call that the difference rule. The limit as x approaches c of f of x minus g of x. What do you think that equals? Because it's inside there, we can split them up. The limit of f of x minus limit of g of x, which makes it L minus M. The constant multiple rule. So if I have the limit as x approaches c of some constant times f of x, because that's a constant, I could take it out of the function. Which makes it k times L. So what this is saying so far is whenever you take the limit, the coefficients are really not that important. You just take the limits with respect to the x values. Then we have the product rule. Basically, all the algebraic functions. The product rule. The limit as x approaches c of f of x times g of x is the limit as x approaches c of f of x times the limit as x approaches c of g of x, which is equal to L times m. What do you think the next one's going to be? We did the addition, subtraction, multiplication. This is going to be the division one. This is the quotient rule. The limit as x approaches c of f of x over g of x but as long as g of x does not equal 0. We can take the limit of the top divided by the limit of the bottom. That equals L over M as long as M does not equal 0. So what this says is we can pretty much distribute that limit function to any part of the equation we want to. It also works with exponents. The limit as x approaches c of the, as long as your function is raised to a power. Notice it's not the whole equation, not the whole limit raised to a power. It's simply the function. So the limit of f of x is L raised to a power. Where n has to be greater than 0. Has to be a positive integer. Why? Because if n is a rational expression, what do we have? If you have a fractional exponent, what do you have? You have a radical. which is what this one is. The root rule. So again, this limit affects only the function itself. So we get remember from algebra, very important, that we can rewrite this as an exponent. This is the root of the radical. It's also, whenever you have that, it's the denominator of your rational exponent. Again, n has got to be greater than 0. So far, so good. Let's look at some examples now. And you're going to see these same things in each chapter we talk about. It'll be done with integrals, with derivatives, even with trig functions. Example 5. Find the following. The limit as x approaches c of x cubed plus 4x squared minus 3. And I'm first going to show you how to do this using the rules we just talked about, and then we'll just jump straight to the shortcut. Because we have the plus and minus signs, we can use the first two rules, the sum and difference rule, which means we can take the limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared minus the limit as x approaches c of 3. So which rule are we going to use in this first one? Motion? The exponent, the power rule, because it's got an exponent. So what does x become? C. Plus, here's a constant multiple, so it goes out in front. And the limit of x squared as x goes to c, it becomes c squared. Minus, what about this last one? What rule is that one? It's going to equal 3. It's the constant rule. That was the second one we talked about. We talked about the identity function and the constant function. So that's a constant. There's no value of x, so it stays 3. And there's your answer. The limit as x approaches c of x to the 4th plus x squared minus 1 x squared plus 5. This is the quotient rule, because it's a fraction. So we take the limit as x approaches c of x to the fourth plus x squared minus 1 over the limit as x approaches c of x squared plus 5. Now we treat the numerator and the denominator separately. Distribute that to each one. So what is it? Let's just jump straight to the final answer. What's the final answer going to be? Any guesses?
C, square root of 1 plus C square root of 2 minus 1. And then C square root of 2 is 5.
Just change all your x's to c's. How about that one? So just put it in place of x, put -2. So we have square root 4 -2 squared minus 3. Square root of 4. -2 squared is 4. 4 times 4 is 16. 16 minus 3. And there's your answer. Yeah. Yeah, because putting into a decimal is just a waste of time. This is more descriptive to me. However, if you can simplify it, if it was like square root of 24, if you could simplify it, then you do so. What do I mean by that? If you had a square root of 24, what is 24 made up of? 6 times 4. So we have square root of 6 times square root of 4. Square root of 4 is, and there's your answer.
Even though the square root of 6 can actually become a 3, right?
No, we can't.
Oh, okay.
Because a square root, when you have a square root, you have to have 2 of the same numbers inside there to bring it out. So that is 2 times 3. They don't have 2 of the same type of number. Let's look at polynomials and rational functions. Polynomial and rational functions. Theorem 2. Limits of polynomials. Actually, for all reality purposes, we've already done polynomials. A polynomial simply means it has many terms. A binomial is a polynomial of degree 2. So what this says is this. If you have some polynomial, we get a sub n x to the power n, a n minus 1 x to the power n minus 1 dot dot dot, a to the first x to the first plus a to the 0. Then the limit as x approaches c of our polynomial function becomes a to the n, c to the n, a to the n minus 1, c to the power n minus 1, dot, 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 a1, c1, a0. So basically, what does that tell us to do? In place of x, put our c value. Guess what? We've been doing that already. Theorem 3. Limits of rational functions. P of x and q of x are polynomials. And of course, q of x cannot equal 0. Then whenever you take the limit of a rational function, what do you think that becomes? Where p and q are both rational polynomials. We learned in theorem 2 that all you do is change x to c. So this one becomes p of c over q of c. And there you have it. What do you think of the difficulty level so far? Non-existent? Pretty easy so far?
Well, it's tricky for us.
No, so it shouldn't even be tricky. It's just whenever you have a limit function, just first step should always be plug in the value in your polynomial, see what happens. Example 6. The limit as x goes to -1. X cubed plus 4x squared minus 3 x squared plus 5. Work that one out. So what do we put in place of x? -1. So we have -1 cubed plus 4 times -1 squared minus 3, -1 squared plus 5. -1 cubed is -1. -1 squared is +1. -1 squared is 1. So we have -1, -3 makes it -4. Plus 4 times 1 is 4 over 6. -4 plus 4 is 0. So the answer is 0. That's the limit. So all it says is as x approaches -1, the y value approaches 0, which gives us our x-intercept. See which other one. Okay, theorem 3, which is the rational. Yes.
But one times -3 equals -3, but not positive 4.
What are you talking about?
On that part right there. Yeah. 1 times -3 is that equal to -3.
Where's 1 times -3?
Right there.
This? That's -1 minus 3.
Oh, okay.
They're not multiplied, they're subtracted.
Yeah, because that's I was confused. I was like, how did you get that number? I was confused. So
Because I'm adding and subtracting. The only multiplication I have is this one.
okay, so it doesn't matter what direction it is at, but you still gotta add.
Combine like terms.
Okay. Just wanna make
If
sure.
the signs are the same, I use this common sign and add the numbers.
Okay. Thank you for that.
Sure.
Wanna make sure.
Example 7. The limit as x approaches 1, we get x squared plus x minus 2, x squared minus x. Because remember, as theorem 3, the rational theorem said if you have a limit of a fraction, p of x over q of x, q of x cannot equal 0. But what happens here? If you have a 0 in the denominator, what do? Because the first thing you want to do is plug in numbers. 1 squared plus 1 minus 2, 1 squared minus 1. 1 plus 1 minus 2, 1 minus 1, 0 over 0. So if you ever have a 0 in the denominator, the first thing you want to do is, okay, don't say that doesn't exist. Always factor out. See if you can remove something. See if you can make it a non-zero denominator. So factor both top and bottom. So we have the limit as x approaches 1, x squared plus x minus 2, x squared minus x. Can you factor out the top? It's a quadratic equation, so let's see if we can factor it out. And same thing at the bottom. It's a quadratic, so let's see if we can factor it out. So review back to algebra. Since our leading terms are x's, we have x in the first spot. Then what do? Well, look at the second sign. Since the second sign's a minus, the only way that could be true is if both signs are opposite. And since the first sign is a plus, the bigger number is a positive. What times what is 2? When you subtract them, you get 1. Yeah, 2 times 1, 2 minus 1. So the 2 goes here, the 1 goes there, because the bigger number gets the bigger number, positive. On the bottom, they both have an x in common. So I take out the x, and I have an x minus 1 left over. Can anything cancel? The x minus 1s. So now our equation is x plus 2 over x. Plug in 1. 1 plus 2 over 1. Our value is 3. So remember, since we canceled out an x minus 1, our whole occurs at which value x? 1. Since we cancel the x minus 1, take x minus 1 set equal to 0. So we have a whole when x equals 1. So we have a whole at 1, 3. Our graph, since we cancel out the x minus 1s, and when we plug in 1, we get a 3. We have a whole at 1, 3. So far, so good. So if you ever have 0 over 0, that means something can factor out. Something's going to cancel. Example 8. Find this limit. Limit as x approaches 0 of the square root of x squared plus 100 minus 10 over x squared. If you put 0 in there, what do we get? We have the limit. So let's put 0 in there. So we have 0 squared plus 100 minus 10 over 0 squared. So we have the square root of 100 minus 10 over 0. Square root of 100 is 10. So we have 0 over 0. That means there's something we could do algebraically there. Can we factor the numerator? No. So how do we fix that? In algebra, you learned a concept called the conjugate. What is a conjugate? we first learned it when we dealt with imaginary terms. If I had A plus B, the conjugate would simply be A minus B. Just change the sign in the middle. That's all the conjugate is. So we have the limit as x approaches 0 of the square root of x squared plus 100 minus 10 over x squared. So what's the conjugate? Do we conjugate the denominator? No, that's not the big problem. So the conjugate is the top number. But remember, we can only multiply by 1. So we have to multiply top and bottom by the conjugate. Because we can't change the equation, we can only change the way it looks. So we multiply the conjugate, the top and bottom. Limit as x approaches 0. On the bottom, we have x squared times square root x squared minus 100 plus 10. So let's look at the top. Radical times radical. This one becomes x squared minus 100 squared plus 10 times radical x squared That's not a plus, that should be a minus. No, it should be a plus. So that says plus. Yes, plus. So it's 10 times 100 minus 10 times the radical. Negative 10, positive 10 is negative 100, or 10 squared. Simplify. The middle terms cancel. The radical disappears. We have x squared plus 100 minus 100. That's that one. All over x squared square root of x squared plus 100 plus 10. The 100s cancel. X squared over x squared square root of x squared plus 100 plus 10. What do I do next? X squares cancel. So limit as x approaches 0. 1 over x squared plus 100 plus 10. 0 squared plus 100. Zero squared is 0 plus 100, so the square root of 100 plus 10. Square root of 100 is 10. 10 plus 10 is 1 over 20. All algebra. What's the hardest part about that is doing the algebra part. A lot of writing, easy to get that mixed up. So the limit does exist, and it's 1 over 20. The next theorem we're going to talk about is very important. It's going to save us a lot of time. The sandwich theorem. What the sandwich theorem tells us is, let's say we have a function that we can't find the limit of. If the limit of f of x is not calculable, then we can find it by comparing it to two other functions. That we can find the limit. So here's what I'm getting at. We have some function like that. We don't know what happens at 0, at some value c. All right, so what are we going to do is we're going to find two functions that we know the limit at 0. One's going to be above there, and one's going to be below there. But they both have the same value at 0. So this is my f of x, this is g of x, and this is h of x. Let's see how this thing works. We know that h of x is less than or equal to f of x because it's below there, which we also know that f of x is less than or equal to g of x. You see how they call it the sandwich? Because f of x is sandwiched between two other functions that we know what the answers are. So if we take the limits as x goes to some value c, of all of these, This is C. Well, then guess what? We know what the limit of h of x is. Let's say in this case, let's say the limit of h of x at C is 0. And we also know the limit of g of x because h of x and g of x have to have the same value. Or instead of 0, I'll put L. They equal some limit. Since h of x and g of x have the same limit and f of x is between there, so what do you think the limit of f of x is? It has to be greater than equal to L, but it also has to be less than equal to L. So that means this one has to be L. That's how the sandwich theorem works. So no matter what f of x you're given, you have to find two functions, one above it, one below it, that the limits exist and are equal. You have to make sure that both the h of x and g of x have the same limit values. That's a good example. Example 10. Let's look at this. We have 1 minus x squared over 4 is less than some value u of x is less than equal to 1 plus x squared over 2. Find the limit of u of x as x approaches 0. How do you think we're going to do this? Set x equal to 0, because that's what it says my limit value is. So we have 1 minus 0 squared over 4 is less than equal to u of x is less than equal to 1 plus 0 squared over 2. Actually, since x is 0, it's u of 0. 0 squared over 4 is 1. U of 0. 1 plus 0 is 1. So the limit of u of x as x approaches 0 has to equal what? 1. Of course, now the hardest part about this are finding the h of x and g of x. Finding two functions that are above it and they have the same limiting value. That's the hardest part. But once you find that, then it's plug and play, you're done. We did that. Yeah, so the rest that's that for that section. What do you think? Pretty straightforward? No, it's not going to be hard. It's just that they're moving parts. Now, we started off last time talking about the difference quotient. How we find the slope of a curve at any one point. Now we're finding limits. Because to find the slope of a curve at a given point, we have to know the limit of that value, because the limit is telling us the slope of that value at that point. Now we're going to go on from here. The next class, we're going to go on further and discuss further definitions about continuity, limits. How do we prove limits? We have to use that by something called the epsilon delta proof. And that's the part you're going to hate the most. But once we finish that, it's going to be easy sailing from there on out. Any questions? Yeah, and I do apologize because